So let's talk about separation of variables, because that's where we're going next. So, and actually, I should say a few more words about this. What I should really say is we're going to solve some differential equations. And in this class, there's really only two ways of solving a differential equation. One of those methods is separation of variables. The other one, which we'll talk about, I think, on Friday, is first order linear differential equations using an integrating factor, which I know is a lot of words, but the process is relatively straightforward. So let's look at some examples of things that we could separate. So we want to solve. Let's not start off with this somewhat challenging one I have over here. Let's start off with a nicer one, James. Oh yeah, right here in front of me. Let's say we want to solve something like this. dy dx equal to 3x squared times e to the negative y. So the first thing we have to kind of ask ourselves is, do we think this is separable? And the answer to that question lies in, can we write the right-hand side of this equation as a function of x times a function of y? Or in other words, can we separate the things with the x's from the things with y's? But specifically, we have to be able to write them as being multiplied together. So just as a counterexample real quick here, I'm going to point out that this differential equation I'm about to write down, dy dx equal to x squared plus y squared, is not separable. The right-hand side there cannot be expressed as things with just x's times things with just y's. And the times there is the important part. So since we can't do that, that one's not separable, we can't use this method, which is fine. We don't need to worry about that. I just wanted to give you the examples of it not separable. So this one definitely is separable. In fact, it's already kind of written in a separable way. We have here some function of x. We have here some function of y. Great. We don't really need to call them f of x and g of y. I'm just pointing out that we have a function of x times a function of y. So when I'm looking at this, I'm always thinking about I want the d whatever is on top. So I'm trying to separate here, since the dy is on top over here, I'm going to bring the y's to the left, and the x's to the right, just because my y's are already on. So this is going to amount to dividing both sides by e to the negative y, and writing 1 over e to the negative y times dy, and multiplying both sides by dx to get 3x squared times dx. And now I've separated my variables. All my y's are on one side, all my x's are on the other side. Great. I would do one more thing before I started trying to solve this. I would rewrite the left-hand side as just e to the y. That's going to be easier to anti-differentiate. So I'm going to rewrite this as e to the y times dy equal to 3x squared times dx. And then I'm going to anti-differentiate both sides of this differential equation. I'm going to do something in this next step slightly out of character just to show you why we don't do it this way, but then we're going to do it the right way. But it's really, what I'm about to do is not wrong, it's just not typical. So anti-differentiating both sides, the antiderivative of e to the y is e to the y, and I'm going to say plus c, although we don't usually put it over there. In fact, I'm going to say plus c1. On the right-hand side, the antiderivative of 3x squared is x cubed plus a constant c2. But then I'm going to write it how we would really write it, which is I can subtract c1 to the other side, and the constant c2 minus the constant c1 is just another constant, which we're going to call c. So really when we're doing this, the side that doesn't have y on it, we're going to put the constant on. So I would have gone straight from here to saying we have e to the y on the left equal to x cubed plus a constant on the right. Question?
You put it on the non-y side in case you want to isolate y.
Right, because typically the end goal here is to solve for y as a function of x, or whatever, solve for whatever your function thing is as a function of your independent variable. It could be y as a function of t, it could be n as a function, right? There's lots of names for things, but basically we're solving for the thing that's on top in terms of the thing that's on the bottom. So then solving here, we're going to take the natural log of both sides and get the natural log of e to the y, which is just y, equal to the natural log of x cubed plus c. That's our solution. Not too terrible. I will point out there's no reason to solve, or I shouldn't say there's no reason. We can't solve for c because we weren't given an initial condition here. So if you're not given an initial condition, this is just the general solution to this differential equation. Let's look at some more examples. No, I should say, are there questions about this before we look at another example? Yeah.
So could that also be written ln of x cubed plus c?
No, definitely not. And here's why.
Is it ln times c?
Oh, I'm gonna stop you right there.
Okay.
We don't have natural log times c. It is the natural log of c. Let me kind of talk about that for a minute because let's say you're correct, it is. That you're not wrong there. But the difference here is that when we have this expression like this, we can't break this apart into two pieces here because we have to add the c, whatever the constant would be, to x cubed before taking the natural log of that expression.
But if it was times.
Right, so there is a logarithm rule that says, right, if we had, like, for example, if we had the natural log of x cubed times c, we then could definitely break this up as the natural log of x cubed plus the natural log of c. We can even go one step further and say that's 3 times the natural log of x plus the natural log of c.
But for the natural log of c, couldn't you just change?
You're right. You're totally right. You could then call this a new constant. Yes, agreed. You can say this is 3 natural log of x plus. I'm going to call it something different just to give it a different name. But yeah, that would be totally fine. Yeah, it's kind of funky how we kind of keep using c over and over and over again. And sometimes the problem here is, like, sometimes when you do something to a constant, it just stays as a constant. So we're like, okay, we're just gonna call it c again. But sometimes you do something like take the natural log of both sides, and then you have to kind of make sure that that constant kind of follows along. So basically, here's the rule of thumb I would follow. If you add a constant to both sides, or subtract a constant to both sides, or multiply both sides by a constant, or divide both sides by a constant, then your constant over here can kind of just stay as a constant. But if you do anything else, like take the square root of both sides, or cube both sides, or anything that's more functional, we typically then have to carry that along. And we'll see that in some more examples. Let's look at this next one. Sorry, keep losing my place here. Sure, let's look at this one. So we want to solve the following differential equation. We have dy dt equal to t cubed over y squared times 1 plus t to the 4th. And do we have an initial condition? Nope. Sure, I'll make one up. Let's say we have that. Yeah, sure. Y of 0 is equal to 2. So there's our initial condition that we'll deal with at the end. Or somewhere near the end. And I'll say, when you're solving for c in your solution to your differential equation, sometimes there's kind of a best time to solve for c. Like, it might not be at the very end. Sometimes it's like, oh, there's c right there sitting all by itself. We might as well plug in our stuff now and find c right then. And I'll talk more about that. That is t to the 4th, yes. All right, so I want everybody to separate these variables. I want you to rewrite this so you have just y's on the left and just t's on the right. That's how things should look. We should have y squared times dy on the left equal to t cubed over 1 plus t to the fourth times dt on the right. Essentially, I'm thinking I'm multiplying both sides by y squared and then multiplying both sides by dt. And now we're going to integrate both sides. The left-hand side should be relatively straightforward. We're integrating y squared. We're going to get 1/3 y cubed. Or y cubed over 3 if you prefer. I'm not going to write plus c on the left. I'm just going to leave it as 1/3 y cubed. And then on the right-hand side, so the right-hand side is a little bit more complicated to anti-differentiate. Depending on how comfortable we are, we could do it without showing the work, but I think we should show the work here. So the work here is to do a u substitution. So I would say, as far as this class is concerned, at least as far as the differential equations are concerned, the two methods of integration you really need to kind of use sometimes, for lack of a better word, is u substitution and integration by parts. Both of those are going to come up semi-frequently. So here I'm going to make the choice to let u equal 1 plus t to the fourth. And the reason I'm making that choice is twofold. I'm choosing that most importantly because its derivative, du dt, is equal to 4t cubed. And I have a t cubed in my integral. That's a really good sign I've made the right choice. The other reason I'm making that choice is because I'm usually trying to pick something for u that is stuck somewhere in the integral, meaning I'm imagining 1 plus t to the fourth is being stuck in the denominator. That's a good way to identify what we want to pick for u. And then I'm going to rewrite this as 1/4 du equal to t cubed times dt. Bringing the dt over to the right and dividing both sides by 4. I'm going to rewrite this integral as the integral of, well, the t cubed dt is going to become 1/4 du. And the 1 plus t to the fourth in the denominator is just u. So I have the integral of 1/4 over u du, or written maybe slightly less terribly, 1/4 times the integral of 1 over u du. That's something we can, and apologies, sometimes my fours look like u's. I will try to make them look as different as I can. That's a 1/4. That's a 1 over u. Okay, then we have to integrate this. We're going to get 1/4 times the antiderivative of 1 over u is the natural log of the absolute value of u. So what I'm doing here is I'm taking this integral and I'm rewriting it in terms of u. So I'm saying I have, sorry, pens. So I have this integral of t cubed over 1 plus t to the fourth d, 1 plus t to the fourth dt. This t cubed times dt is equal to 1/4 du. And this 1 plus t to the fourth is equal to u. So we're integrating 1/4 1 over u du, which then becomes 1/4 times the natural log of the absolute value of u plus c. And then we plug back in the u, and watch here for a second. I'm going to rewrite this as 1/3 y cubed equal to 1/4 times the natural log of, I'm not going to write the absolute value, and here's why. U is equal to 1 plus t to the fourth. 1 plus t to the fourth is always positive. So there's no need to write the absolute value. And you will see solutions in textbooks do this a lot. There was an absolute value and there's not after that because the thing that you're taking the absolute value of is already always positive. So there's no need to write the absolute value there. Totally fine. Yeah, it's totally correct to still write it. I just want you to see that people are going to do this as well. Okay, so now I'm going to try and solve for y, which shouldn't be too terrible. So first, I'm going to multiply both sides by 3. I'm going to get y cubed equal to 3/4 natural log of 1 plus t to the fourth plus 3 times a constant is still a constant. And this might be where I would choose to find c, but let's go ahead and just find y and do c part last. So then to solve for y, I'm going to take the cube root of both sides. So if I have y cubed equal to 3/4 times the natural log of 1 plus t to the 4th plus c, then y is going to equal, you can either write it all to the 1/3 power or the cube root of. I kind of like the cube root notation personally. The cube root of 3/4 natural log of 1 plus t to the 4th plus c. And that is our general solution. To find the particular solution, we're then going to plug in our initial condition. So our initial condition was, again, y of 0 equal to 2. Or if you prefer to write it a different way, you can write it as t equals 0 and y equals 2. So we're just going to plug those things in and solve for c. So now, if you look at these equations here, you might notice it's probably easier to plug that stuff into this equation with the y cubed equal to that stuff as opposed to this equation if we're trying to solve for c at some point. So I'm probably going to plug in right there just because I think it's easier. So plugging in y equal to 2 and t equal to 0, I'm going to get 2 cubed equal to 3/4 times the natural log of 1 plus 0 to the 4th is still 0 plus c. Yes.
Y equals plus or minus.
So that would be true if it was a square root. When we take
Right.
or any even root. When you take an odd root of something that retains the sign, so you don't need a plus or minus. Like I could write it as y equal to all that stuff to the 1/3 power. That's another equivalent way of writing it. Yeah. All right, so now 1 plus 0 is 1, and the natural log of 1 comes up a lot. Natural log of 1 is 0. I would highly encourage everyone to have this kind of working graph of the natural log of x just in their head. It's not the best picture I've ever drawn, but there's your y equal to the natural log of x. It's got a vertical asymptote at x equals 0, and it has an x-intercept at 1, 0. So if you plug in 1, the natural log of 1 is 0, which is great because then it means it's really easy to find c. C is just going to be 2 to the 3rd, which is 8. And this is where I see so many students fail to finish the problem. So then we have to write the particular solution. The particular solution here is going to be that same general solution, just with the c value substituted in. So we're going to get y equal to the cube root of 3/4 natural log of 1 plus t to the 4th plus 8. Thoughts about this? Mm-hmm. Sure. Yes. In fact, so let's go back. Yeah, you make a good point. So if we look here, so I solved for c at this juncture right here, but I could have solved for c right here. Now, here's what I'm going to do. I'm going to say that this is c. We're going to call this C1. Oh, sorry. Yeah. Sorry, I keep thinking you can see because it's the light check. So that I'm going to call that C1, and then still C1 here. I haven't changed it. I just rewrote things. But then I multiply both sides by 3. So this is a new constant. I'm going to call it C2. So this is a new constant. I'm calling it C2, C2. So C2 is 8. But I could have solved for C1 right here, and if I had, here's what would have happened. Running out of room. So if instead I said I'm going to solve for C1 right there, where I have 1/3 y cubed equal to 1/4 natural log of 1 plus t to the 4th plus C1. And if I plug in t equal to 0 and y equal to 2, look what happens. On the left-hand side, I get 1/3 times 2 cubed. On the right-hand side, I get 1/4 times the natural log of 1 plus 0 plus C1. Natural log of 1 is still 0. So in this case, I get 8/3 equal to C1. And so then this would have been 8/3. And then when I multiply both sides by 3, 3 times 8/3 gives you 8. So that's what's happening there, which is why we can kind of ignore it, because it gets accounted for at the very end, essentially.
Solve for it there.
Right.
You can't plug 8/3.
Correct, because 8/3. So we're solving for it. So then we would go back and say, well, okay, I'm going to plug it in right there. So then my equation is 1/3 y cubed equal to 1/4 natural log of 1 plus t to the 4th plus 8/3. And now this isn't just some generic constant, it is actually the number 8/3. So then anything we do to both sides, we actually have to do it to that number. So then in the next step, I multiply both sides by 3. And I get y cubed equal to 3/4 natural log of 1 plus t to the 4th plus 8/3 times 3, which is 8. And then I take the cube root of both sides, and I get y equal to the cube root of all that stuff. Plus, I still end up with the same answer. Again. Yeah, sometimes they do. Sometimes questions will ask that. Yeah, and that's where things get a little bit weird, I will say. I would say, I mean, so yeah. So I guess here's how I would phrase it. I would leave the constant alone until I had gotten y by itself. So if they're asking that kind of question, I feel like you have to kind of find the general solution first without solving for c. So our general solution, looking like this. And then we can say, okay, then what does that c value there actually have to be? So that's the constant.
So it'd be like
No, the constant here is 8. But yeah, it's kind of funky. And I say that question usually gets asked for problems that are maybe less finicky. Good questions. Other questions? Let's look at this time here is so misleading. Okay. Let's see. Let's look at. Yeah, we can try that one. Let's say we have the following. Make sure you can see what I'm writing. Y prime equal to, sorry, not equal to, minus 6xy equal to xy squared. At this point, we are kind of fully just, every time we see something, and I would say this is generally true, every time we see something, we should first try to do separation of variables, because usually it's the easier method of solving a differential equation. It's kind of like in 16b, when we were doing integration, we would almost always try to do u substitution first because it was usually the easiest thing to do. And sometimes it would work, and sometimes it wouldn't. And then we try other stuff. Same idea here. I'm going to try to separate. And if I'm going to try to separate this, the first thing I have to do is bring everything that's not y prime to the other side. So I'm going to rewrite this as, I really actually don't want to write it as y prime, but I'm going to. I'm going to write this as y prime equal to xy squared plus 6xy. But I really would rather use the other notation for the derivative. Not y prime, but dy dx, because that's going to show me how I want to separate things. I'd rather write this as dy dx. And now the question is, can I write the right-hand side as a thing with just x's times a thing with just y's? Or a better way to ask that question is, can I factor out either the x's or the y's from the right-hand side? And in my opinion, it looks like I can factor out an x from both of those things. I would write this as x times y squared plus 6y. Because
Oh, we don't want that.
right, but what's the answer to my question? Why don't I want that? Exactly. I want the x's and the y's. They're not friends. They want to be separate from each other. So then we're trying to bring the x's to the right-hand side and the y's to the left-hand side. Whenever I'm writing this, I'm always putting the derivative on the left. And so whatever's in the top is always going to end up on the left. And whatever's in the bottom is always going to end up on the right. But basically each d whatever thing has to end up not in the denominator. So I want to say, okay, on the right-hand side, I'm going to bring that dx over and I'm going to have x times dx. On the left-hand side, I'm going to have division by y squared plus 6y. So I'm going to have 1 over y squared plus 6y dy. And then we're going to anti-differentiate both sides. Okay, so we're going to have the antiderivative of 1 over y squared plus 6y dy is equal to the antiderivative of x times dx. The right-hand side's fine, and anti-differentiating x is pretty straightforward. It's going to be x squared over 2 plus. The left-hand side's a little bit of work. Yeah.
Just do y squared plus 6y dy equals 1 over x dx.
Well, I don't think that's an option. The thing, so here's the thing. It's something, so we can't bring the x's to the left here, because if we brought the x's to the left, we'd have 1 over x times 1 over dx. And that's not going to help us. 1 over dx is a problem. We don't want, and also on the other side, right? We'd have y squared plus 6y times 1 over dy. Yes, I much would rather prefer to integrate y squared plus 6y as opposed to 1 over y squared plus 6y, but it's not an option. So to integrate this left-hand side here, well, I can't do a u sub. It's not just the natural log of that stuff. Good question. Why can't I do a u sub?
Is u sub like chain rule?
Yeah, no, u sub is like you're undoing the chain. Yeah, you're looking, basically, you're looking for the stuff in the chain rule that you end up taking the derivative of. So like you want the, like, it's kind of like if you take the derivative of sine of x squared, you get cosine of x squared times 2x. The inside x squared thing is the thing you're looking for as your u, because the derivative is also hopefully showing that. So here's the reason a u sub is not going to work out for us here. The only real plausible choice for u is y squared plus 6y. But if u is equal to y squared plus 6y, the du is the derivative of that, which is 2y plus 6 times dy. And I don't have anything close to a 2y plus 6 on the top, so I'm out of luck. So u sub doesn't work. It's not the natural log of that stuff, because if it was the natural log of that stuff, the derivative would be 1 over the stuff times the derivative of the stuff. I'll point out, just as a quick aside here, if we were integrating 2y plus 6 over y squared plus 6y, then the antiderivative would be the natural log of the absolute value of y squared plus 6y. Because the derivative of plus c, because the derivative of that would be 1 over that stuff times the derivative of that stuff, which is exactly 1 over y squared plus 6y times 2y plus 6. But it's definitely also the reason why the antiderivative of this is not the natural log of y squared plus 6y. So unfortunately, this means we have to use partial fractions, which has probably been a little bit of a while since you talked about partial fractions. Talked about, right, 16b, we talked about partial fractions? Pretty sure. Yeah, I'm fairly sure we do. They come up occasionally in this class. I have to imagine Professor Burke wouldn't let you get away with not doing a problem with them. So we're gonna do one example here. We'll talk about it. So partial fraction decomposition. How do we integrate 1 over y squared plus 6y? So there are 3 things we need to be true to be able to use partial fractions. Thing 1, the thing we're integrating has to be a rational function. Just meaning it's a polynomial divided by another polynomial, which this is. Thing 2, the degree on top, the highest power on top has to be less than the highest power on the bottom. Also true. And the third thing, which is really important, is you have to be able to factor the denominator, which we can. We can rewrite this as 1 over y times y plus 6. So then we're just going to do some algebra that is not calculus at all. We're going to take our fraction here, 1 over y times y plus 6, and we're going to write it as the sum of two fractions that have less complicated denominators. Specifically, something divided by y plus something divided by y plus 6. And the reason those are the things we're writing is because you could add these together. You could get a common denominator by multiplying this part by y plus 6 over y plus 6 and this part by y over y to get whatever that is. But the problem here is, the thing we have to work on is we don't know what the numerators are. So we're going to call them a and b, and our job here is to solve for a and b. More generally, when you're doing a partial fraction decomposition, you're essentially writing this fraction as a sum of a bunch of fractions that have each factor as its own individual denominator. It's slightly more complicated when you have factors raised to higher powers, but we'll talk about that if we need to. All right, so here's what we do next. We multiply both sides by the common denominator. So I'm going to multiply both sides by y times y plus 6. The whole point of this step is just to get rid of all the denominators. So when we multiply it by the left-hand side, we get 1. When we multiply y times y plus 6 times a over y, the y's are going to cancel. And we're going to get a times y plus 6. Similarly, when we multiply y times y plus 6 by b over y plus 6, the y plus 6's are going to cancel, and you're going to get b times y. There are there's like 2 or 3 ways to solve equations like this. Let me show you the way that I think is the easiest. The easiest way to solve this is, this equation is true for any value of y, or at least it needs to be true for any value of y. So we're going to pick the most convenient values of y. I'm going to pick y equal to 0. Why am I picking y equal to 0? Because if I pick y equal to 0, this term goes away. And then you get 1 equal to a times 0 plus 6 plus b times 0. But anything times 0 is 0. So I get 1 equal to 6 times a, which means a is equal to 1/6. Great. What other value of y can I pick that'll make the other term go away? Exactly. So I'm going to pick y equal to -6. Substitute that in and get 1 equal to a times -6 plus 6 plus b times -6. Again, something goes away, and I can solve for b really easily by dividing both sides by -6 and get -1/6 equal to b. So then we can go back and say, oh, I don't have to integrate this anymore. I can integrate 1/6 divided by y plus -1/6 divided by y plus 6. So the antiderivative of 1 over y times y plus 6 is equal to the antiderivative of 1/6 over y plus -1/6 over y plus 6. I would probably choose to factor out a 1/6 just because it seems easy to do here. It's not really necessary. And get 1/6 times the integral of 1 over y minus 1 over y plus 6. And finally, well, not finally, because we're not done yet, but finally, for this part, we can integrate both of those things. The antiderivative of 1 over y is the natural log of the absolute value of y. The antiderivative of 1 over y plus 6 is the absolute value, is the natural log of the absolute value of y plus 6. And I guess we don't really need the plus c, but right. Kind of complicated, but it does come up occasionally. So now we're going to go back and we're going to solve the differential equation. So I'll remind everybody, we were solving this. We were solving the integral of 1 over y squared plus 6y dy equal to the integral of x dx. That's what we were trying to solve. We just integrated 1 over y times y plus 6 and got all this. So I'm not gonna write the plus in, write the plus on the other side. So here's what we have. We have 1/6 times the natural log of the absolute value of y minus the natural log of the absolute value of y plus 6 equal to the antiderivative of this, which is x squared over 2 plus c. And if I was feeling lazy or taking a test and didn't have a whole lot of time, I might just stop there and not actually go through the process of solving for y because it's a little complicated. And also I should say, you will have some differential equations where you can't actually solve for y at the end of the process. Happens that way sometimes. Here we can, if we use our rules of logarithms. So here, if we combine, well, actually, first I should multiply both sides by 6. That seems like the smart choice. But I'm also going to combine this. The natural log of the absolute value of y minus the natural log of the absolute value of y plus 6, I can rewrite as the natural log of the absolute value of y divided by y plus 6. Right? The rules for logarithms, if you subtract two logarithms, you can do the first thing minus, or sorry, the log of the first thing minus log of the second thing becomes the natural log of the first thing divided by the second thing. And then if I multiply both sides by 6, on the right-hand side, we're going to have 6 divided by 2, so 3x squared. And 6 times a constant, still a constant. Okay, I'm trying to solve for y. I'm going to exponentiate both sides. So I'm going to say e to the this is equal to e to the that. On the left, I get y over y plus 6 in absolute value. On the right-hand side, I get e to the 3x squared plus c. Okay, a few things happen here. And this is actually kind of important because here's what I really want to tell you. You can almost always ignore these absolute values. Here, watch y. So I'm going to rewrite the right-hand side. E to the 3x squared plus c is e to the 3x squared times e to the c. And then if I drop the absolute values, so what this really means, if the absolute value of y over y plus 6 is equal to this, it means either this stuff could be positive or this stuff could be negative. When we take the absolute value of it, it's going to come out positive, which makes sense because this stuff here, e to the anything, think about the graph of e to the x. E to the anything is always positive, right? The graph of e to the x does this, it's always above the x-axis, so it's always positive. So it makes sense that this should always have to be positive. But maybe the insides were negative. So here's what we're going to say. We're going to say that y over y plus 6 is equal to plus or minus e to the c times e to the 3x squared. And then here's the trickery that always feels like it's just a lie, but it works, is that plus or minus e to the c is just a constant. And we're going to call it, people call it either C. I often call it capital A just because I feel like it's good to change it. So we're going to say, great, y over y plus 6 equals a times e to the 3x squared. And then we're going to solve for y, which seems like terrible, but we're almost there. Yeah, we're almost there. Sure, we're almost there. So we multiply. Yeah, question. Because we're saying a is either the positive or the negative value, whatever the constant happens to be. Right. It feels like we're kind of cheating the system, but we're not. It totally works. But the end result really means that when you get to here, you can kind of just ignore the absolute values, because if you ignore the absolute values, you would still get down to saying y over y plus 6 equals some constant times e to the 3x squared. But yeah, I get your reticence. It feels kind of like, why don't we need the plus or minus there? Well, because this a is really accounting for it. A is equal to either the positive or the negative e to the c, whatever it happened to need to be if we had an initial condition. But yeah, it feels a little shady. All right, so solving for y feels like kind of an exercise in terribleness, but we're going to multiply both sides by y plus 6. We're going to have y equal to y plus 6 times a e to the 3x squared. We're going to distribute. we're gonna get y equal to y times a e to the 3x squared plus 6a e to the 3x squared. We're gonna bring that term over there to y minus y times a e to the 3x squared equal to 6a e to the 3x squared. Factor out a y. We have y times 1 minus a e to the 3x squared equal to 6a e to the 3x squared. And finally, divide by that to get y equal to 6 times a times e to the 3x squared divided by 1 minus a times e to the 3x squared. Yeah, it's kind of a terrible thing. I would say this is definitely on the harder side of separating variables. Right? This is probably one of the hardest separation of variable problems you will hopefully encounter. Or not encounter. Yeah.
So like, that's okay if we put our answer or?
Well, so sometimes it's necessary. So for example, this problem was we weren't given an initial condition, so we don't really have a choice. So yeah.
I mean, like, it's kind of like something that we invented, like, do we not need to put it back in terms of?
No, we don't. And I'll tell you, this process here is really widely, like your teacher, if you did this, Professor Bird would be like, yeah, of course, they did the normal thing. Like, this is what everyone does when they do this. So what I'm doing here is not anything special or out of the normal. Everyone is doing it this way when they do problems like this. So don't feel like you're like breaking the rules or anything. It's no, this is the process that everyone uses.
Right, that A equals.
Nope, everyone's gonna know that that's what you mean. Right, I know it's kind of weird, but like, or some people use capital C. Some people, yeah, it really like. I think A is kind of the general term that people use, but you might watch if she does something like this to see what she does. I didn't see. I was looking at her notes from class, and I don't think she did any examples that were like this. Double check here. Yeah, I didn't see anything that was like this in her notes, which is fine. Maybe she's trying to make it not terrible for you all, which is lovely. But yeah, she definitely avoided that, which is again. Okay. Well, so let's say we had an initial condition here. Let's go and say at the end of the day, great, someone just told us our initial condition was that when x is equal to 0, going to find yeah, that y is equal to 12. So then we can go and find a. So if we do that, we're going to say, well, great. 12 is equal to 6 times a times e to the 0 over 1 minus a times e to the 0. So in other words, so again, here's a time where it might have made sense to not plug it in right here, right? It might have made way more sense to look right here and be like, oh, if I plugged in y and x there, it's going to be a lot easier to solve for a. So I could do it this way and say 12 equals 6a over 1 minus a. But instead, I could be smarter about it and be like, well, if I just start right there instead, I'm going to have y equal to 12. So 12 over 12 plus 6 equals a times e to the 0. Well, that's a lot nicer. 12 over 12 plus 6 is 12 over 18, which is 2/3. So 2/3 is equal to a times 1. So a is 2/3. Which is also true, right? If I do it here, if I actually solve this, I would have 12 times 1 minus a equal to 6 times a, and then 12 minus 12a equal to 6 times a, and then 12 equal to 18a, and then 12/18 equal to a, which is also 2/3. But that's kind of what the point I was trying to make before about picking the right moment to find your constant. If you are having to find the constant, look for the place where the constant you're trying to find is kind of as isolated as possible. It's going to be easier to find it. Whereas here, there's a lot more work to do to actually find a after I plug in x and y.
So.
Right. Correct. So then our particular solution for x equal to 0 and y equal to 12 of the differential equation we started with, which was way back so many pages ago, of y prime minus 6xy equal to xy squared is going to be y equal to that solution, which you can't quite see, with 2/3 plugged in for a. It's going to be 6 times 2/3 times e to the 3x squared over 1 minus 2/3 times e to the 3x squared. And it's pretty typical to multiply the top and bottom by 3 here so that we don't have fractions and fractions. And if we do that, we're going to get y equal to 6 times 2 is 12 e to the 3x squared over 1 times 3 is 3 and 2/3 times 3 is 2 e to the 3x squared. That's probably the most typical way of writing the solution to this differential equation with these initial conditions. Okay, time. It's 1:58. I probably shouldn't start another example. So here's what I'll say is coming up next class. So the other type of differential equation, which we're going to learn how to deal with, is one that requires a method that's called an integrating factor. So we're going to look next time at solving differential equation like the following: dy dx plus, I don't want to make it too terrible, 4xy equal to e to the x. And so something like this, you can't separate, right? This is not separable. But there is a method which requires us writing this. So to write this as a first order linear differential equation, and by the way, just to explain what these words are, first order means you only have a first derivative. You don't have a second or a third or a higher power derivative. Linear because the only power of y is y to the first. You don't have a higher or other not first power. That's making it first order linear. And what you're going to do is then you want to write this as y prime plus some function of x times y equals to some other function of x. So that's the first step in solving a first order linear differential equation. And this one's already written that way. So this one is written as y prime plus some function of x equal to some other function of x. And I'm sure you'll talk about how to do this in class on Friday, but we will also talk about it. Cool. Continue all. I have office hours over in CADS in like 15 minutes, and see you on Friday.